So question 1 asks you to find the domain and range of the following function. So in this function, we have, first of all, looking at the domain, we look at the lowest x value, which seems to be negative infinity, because you can tell by this arrow that keeps on going towards infinity. Then we have a bit of a break here where that particular value there is x equals to negative 2. But then you have this point up here, and that point actually means that the x value of negative 2 still exists. So this graph continues going on up to this point here. Now at x equals to 1, there seems to be a break in the function. Remember, the open circles are not inclusive. And then the graph continues on. At 4, there's a gap as well, but 4 is actually included in the domain because the x value can be still 4. That part of the graph means that x is not going to be 4 for that particular fragment of your graph, but in general, the function does contain the x value of 4. So the domain, we write x is an element. We know we start from this side here, so we know that this part of the graph goes up to infinity, and it goes up to negative infinity. So we open brackets, negative infinity, up to. Negative 2 is still included. Okay, so we don't even mind. We can just contain negative 2, but we can see that there is a problem around here. There is a gap. You're not allowed to have the value of 1. So at 1, we're going to keep the bracket. We're going to have this type of bracket, which means excluding 1. And then it starts off again at 1. This function starts off. So this one here, this branch starts off. But again, that branch starts off by not including the value of 1. So it's union 1 up to an x value of 4. And you are including 4. And actually, because you are including 4, you then look at the next part of the bracket and the next part of the graph, and that seems like it's going all the way up to positive infinity. So you don't actually have to break up the function here because it's still clearly going to be including the value of 4. So you can actually directly just say, that that's infinity, circular bracket here. So that's one way of expressing it. Another way of expressing this domain would be x is an element of all real numbers except the value of 1. So that value is the one here that was problematic because 1 was not included in the domain at all. So that's the domain for the function. Okay, so our domain is here. Now our range, for our range we need to look at a different perspective, so I'm going to get rid of all these squiggly things that I've drawn on my graph. Okay, so for the domain we're looking at the minimum value. So we can see that if I just kind of slide this down a little bit, we can see in the graph that negative 4 is the smallest possible value that you can get for your y. So we will go negative 4. Okay, before we do that, actually, I'm just going to think about what my y values are doing. So this part of my y equation is going up to infinity. And that bottom part, although, yes, negative 4 is clearly the lowest point, this graph here, this portion of the graph will probably keep on going down. And so that's going to go lower than this negative 4. So it's actually negative infinity. Okay? Now, this portion, there is a gap here, but that portion is still included in this part of the graph here. So although you have a gap there, you don't really mind that there's a gap because that gap is accounted for on this side. So you don't need to state that there's a range missing, that there is a region of Y values missing, nor do you have to really comment that there's a set of Y values missing here, because this graph will eventually, as you can see, this graph is going down, so eventually it will make up the difference of Y values here, so it will seal that gap. And so it seems as though the whole range is actually going to just be Y is an element of all real numbers, that there's actually no numbers that are not included in the range. All Y values are included. It's just that certain sections of the graph don't have Y values, but that's accounted for in other sections of the graph. And so you don't need to worry about the range of those increments. Okay, so that was the first type of question. Our second question here states the function of Y equals to 2x cubed in the domain of this undergoes the following transformations. So first of all, it's reflected in the y-axis. So reflection in the y-axis means that if you have a graph right here reflected in the y-axis, here's your y-axis, it means that that graph is mirrored on this side of the equation, of this side of the quadrant. And so what has happened is that our x values, they were positive x, now they become negative x values. And so what you need to do for your function is you need to find the transformed function of g of x. So g of x is equal to, first I'm going to account for the reflection. So with the reflection, I need to make my x values go from positive to negative. So what I'm going to do is I'm just going to go, okay, well 2, and then put in negative x, because we're making our x values negative, cubed, and that's accounting for the reflection. So we've done the reflection in the y-axis. Now, we have to look at translation 4 units up and 2 units in the negative x direction. So 4 units up means that y is equal to 4, and 2 units in the negative x direction means that x is at negative 2. And so when you're putting it in the translation into the equation, you need to make sure that that negative is for your x values. If you move the negative 2 over to the other side, it becomes positive 2, and then you can turn it into a set of brackets. So what I'm going to do with my x translation, I'm going to put that into brackets. So I'm going to write x plus 2. I'm still going to keep the cubed on the outside, and then my y value has directly just been affected by a positive 4. So I'm just going to write positive 4 on the outside there. So that accounts for the translation. And then dilated by a factor of a third from the x-axis. So if we change it by a factor of a third from the x-axis, what that means, here's our x-axis, we're dilating it by a factor of a third, so that influences our y values. And so our y value is everything outside of the x bracket. So what we need to do is we're going to have to multiply the whole equation by a third. And then we've got 2 minus x plus 2 cubed plus 4. Remember that factor, because it was the last thing that happened, you have to multiply each and every one of these values by a third. And so what I'm going to do to get the proper equation is I may try to expand that. Actually, even better than expanding it, I may try to, sorry, I don't know why I put those double dashes. I may try to factorize or take out a common factor of 2 from inside of here. So I'm going to write 2 over 3 bracket negative x. I may as well expand that negative there. cubed plus, I've taken out a 2, so that's 2 now. And if you really want to, you can multiply those values in and take out a minus from here. Because it's a cubed, you can take out a minus. So you can go minus 2 over 3 x plus 2 cubed, and then multiply this by that value there, which is going to be plus 4 on 3. So this is our new transformed g of x function. Okay, so that's our transformed function. And question B asks us, express the function g of x in function notation. So function notation was like when we had g dot dot, then we had the function, so then we had the domain, and we had the codomain, which was r, and then you wrote comma, and you wrote the function out. So you would write negative 2 over 3 x plus 2 cubed plus 4 on 3. And so we need to find the domain. Now, because the graph has been shifted, has been moved in a different axis, in a different quadrant, it's been translated across, has been dilated by a certain factor, the domain can change. So the original domain, your original domain was x is an element from negative 1 to 5. Okay, now the changes that have occurred is we had reflected the whole graph in the y-axis. So what that means is that these values, so you had a value, say a point at negative 1 and at 5, actually at negative 1 it was a closed circle, sorry, an open circle. And at 5 it was closed circle. And so we've swapped them around because our value here has been reflected around the y-axis. So here's our y-axis. Now that point is at negative 5. So it's right here, and it's still closed, except it's just been reflected around the y-axis. And that value there has been also multiplied by a negative number, so it's become positive 1. So it's now there. So just through the reflections, the effect of the reflection, x is an element now from the lowest number is negative 5, the highest number is 1. Okay? So that's the first point. The second point is it's been translated up by 4 units. That doesn't affect our domain. However, our domain will be affected by the next change, which is a change of 2 units in the negative x direction. So if you consider moving both of these points 2 units in the negative x direction, you're subtracting 2 from them. So now the domain is going to be x is an element from negative 1 minus 2 is negative 3. Sorry, it's these. I should really label these carefully. It's actually these values up here. So minus 2 and minus 2. If you take the negative 5 and you subtract 2, you get negative 7. And if you take the 1 and you subtract 2, you're going to get negative 1. So the new domain will become negative 7 and 1 take away 2, which is negative 1. And you still keep an open circle there. And finally, we have a dilation by a factor of a third from the x-axis. That will actually only influence our y values, because I showed you before that the arrow is actually going from the x-axis, which indicates changing y values. So our domain, when we're writing the function notation, we can now write our domain up to, we can say, okay, well, it's negative 7 and negative 1. And that becomes our function notation right there. This whole thing is what you're looking for in this question. Okay? Let's have a look at the next one. The range of the transformed function. So the range, you can see that you have certain endpoints here. So I would suggest just substituting those endpoints into the function. So you've got, g of, first we could put in -7, so -2/3, -7 plus 2 cubed, plus 4/3. That's going to be -2/3 times by this part, which is -5 cubed plus 4/3, sorry. So you can work out that value there, which is going to take a long time. That's 125. That's 125. It's -125, and then it's divided by 3. It doesn't really work. So 125 times by 2, which I should really know, that's 250, because these two are multiplying. That will become overall -3 plus 4/3, which is equal to 254/3. So that's the y value, and then the other value, g of -1, is going to be equal to -2/3 minus 1 plus 2 cubed plus 4/3. So that's actually -2/3 times by -1, no, plus 1 to the power of 3 plus 4/3, and that gives us -2/3 plus 4/3, which is only going to be 2/3. Okay, so what that means is our function here, now this came from the value of -1, so this is not going to be included. This value is not included because it came from a circular bracket. And this value here came from -7, and as you can see, the bracket in front of -7 is inclusive, so this is going to be included. Now when you write out your range, you just go g of x is an element from the minimum value. Now the minimum value is 2/3, and it's not included. So circular brackets up to 254/3 included. Okay, so that becomes our range. All right, now question 3. Question 3 states a parabola is formed by joining 3 points below, and you have to find the equation and domain of the parabola. So this needs to be all connected. So it's going to be kind of like this. If I draw a parabola, there we go. Okay, state the equation, the domain of the parabola. Now, so it looks like these points are inclusive, the endpoints. So I'm just going to read what that point there is and what this point here is. So I can already find the domain. X is an element from the minimum number, which is inclusive of -7, up to the maximum number, which is 5. And that's included. So that's the domain. We've done that. We also have to find the equation. So this looks like we can read the turning point. The turning point is there and down there. So the turning point actually of this function is 1 and -3. 1, 2, 3, yep, -3. So the turning point of our equation of our parabola is 1 and -3. And what we can do with that is we can actually put it into our equation. So x, remember with the turning point, you just go, okay, well, the x value of the turning point is 1, and the y value is -3. And because x exists in the bracket in the equation, you need to go x minus 1. bracket like that. So when you're putting that turning point back in, that's why it becomes -1 squared and then -3 down there, because it's y equals to -3. Now that we have those points, it may be important to find your dilation factor, to find the value of, say, A. Now, what we can do is we can use another point. We can use this point here, which looks like a intercept, so use 5 and 0 to find A. So we're going to go, okay, well, 0 equals to A, 5 take away 1 squared -3. So carry the 3 over to the other side. So 3 equals to A, this is 4 squared, so 16. And A is equal to 3 divided by 16, which we can then find the equation for. So y is equal to 3 over 16 okay? So that's the equation of a parabola. We may need to put it into a specific form, but for this question, it's okay. It's completely appropriate to put it in turning point form. That's fine. Okay. So, question 4. Question 4 states, for the polynomial of this, show that this is a factor. So what you're using here is you're using the factor theorem. Now, to work with the factor theorem, first of all, you're starting off with this particular bracket. You're setting it to be 0. So you're turning the factor into a solution form. So you're carrying the -1 over, you're going x equals to -1 over 3. Now, with this, you're actually replacing p of x up here with -1/3. And you're writing 3 times by -1/3 to the power 3 plus 2 times by -1/3 squared minus 17 times by -1/3 minus 6. Okay, and what you end up with is you end up with, this becomes -1 over 27, so 3 times by 27 with a negative on the outside. This becomes plus 4 over 9 plus 17 over 3 minus 6. And all of that, when you add it up, that should give you 0. Okay, so the factor theorem, if you use the solution and it gives you a y value of 0, you have just shown that, therefore, 3x plus 1 is a factor. That's called the factor theorem. Okay? So, then we have to factorize the expression by long division. So we'll have a bit of work to do here. Let's have a look. Why has my screen shifted? Okay, so we've got 3x plus 1, and we're dividing the entire polynomial by that expression. So our polynomial is 3x cubed plus 4x squared minus 17x minus 6. So now we go through the process. So we can take this first term here in the actual polynomial and divide it by 3x. And what we'll get is, when we do that, we get x squared. So x squared times 3x is 3x cubed, and x squared times 1 is plus x squared. Now, whenever you get to that end, when you multiply this term up here by each of those terms, you're finished that very first line. You subtract the terms from one another. 3x cubed minus 3x cubed just cancels. And 4 take away 1 becomes 3x squared. And then we drop each of these values down in the next line. Okay, so now we've got our new expression. So once again, we go through the process of something times 3x, that gives you 3x squared. So that's actually plus maybe x. We multiply by those two terms there. So our aim is to always get the first term to be identical so that you can eliminate it. This x comes from timesing multiplying x by the 1. You always subtract in long division. Negative 17 take away x is negative 18. X minus 6. And then once again you have to, well, maybe it's minus 6 now, because minus 6 times by 3 gives you minus 18 x, and then minus 6 times by 1 gives you minus 6. Again, you draw a line, you draw a subtraction sign, and finally we get the same content, take away the same content will give you always 0. And 0 is what we expect, because remember when we just worked out a second ago what this particular value is, we got 0. And so that needs to be the same as the remainder. Okay? So you can see that the remainder is 0, so that means that we're doing everything right. So our polynomial, p of x, is the same as 3x plus 1. And then what we do is we take this expression up here and we are going to be factorizing that. So x times x, and then 6 breaks down into 2 and 3, and then you want to create plus 1, so you have to put the minus in front of one of these, then double check. So x times 3 gives you 3x, x times negative 2 gives you minus 2x, which gives you x. So we know that this is a bracket and so is that. So what we do is we just plug it into our formula, x plus 3. So that's our polynomial there. Okay, that's all nicely factorized for us now. Then you might be asked to sketch it, but for this question you're not. Okay, question 5 asks you to find the equation of the following. So this is a parabola, seems to cut through this point and also this point here. So that point up there, the turning point, seems to be at the coordinates of 1 and 3. 1 for x and 3 for y. And then the y-intercept from that graph looks like it's 0 and 2. And once again, we use turning point form. We are going to be using the x value there, so x is equal to 1. And then when you put it into a bracket, x, it becomes minus 1. Okay? And then the y value is just directly 3, positive 3, so we write plus 3. And then we need to use our y-intercept in order to substitute into our function here. So 2 equals to a 0 minus 1 squared plus 3. And this is all in the aim of finding a. So we move that 3 over to the other side. That becomes minus 1. And a becomes equal to minus 1. So therefore, our equation is y equals to minus x minus 1 squared plus 3. Okay, so that's our equation of the parabola. Okay, question B. Question B looks like a fairly tricky one. You've got a turning point at that location. What we need to do is we need to find all the solutions. So one of the solutions, it seems as though the graph goes through the point 0, 0, also goes through this point, and it also goes through this point here. So x becomes equal to 0. The other x value is equal to 1. And the last x value is equal to, where is it? 3. Now, this is just as a factor, just because this is a bit confusing. As a factor, that turns into just x on its own, because when you move the 0 over, it's just x. Now, this solution here, when you move it over to the other side, x minus 1, that, remember, was if you look at where it is, it's actually a turning point form. So you need to, really important, put a squared around that factor, because it's turning at the axis. And then this one here turns into x minus 3. So your equation becomes fx equals to x times by x minus 1 squared, x minus 3. Okay, so that's our equation. And I will not be assuming that there's a factor here. There could be, but in this case, I'm just going to leave it as that. This question was meant to say that the dilation factor of the graph is equal to 1. Okay? So that's that question. Now, let's have a look at these two. So, we might need a little bit more space. A line is perpendicular to this line. So, a line, y equals mx plus c. We don't know what it is. But we do know that it's perpendicular to this one. So what we need to do with that is we need to get it into y equals mx plus c form. So currently it's not, but slowly if we can move that term over to the other side, and then we can divide everything by -3, we get 2 over 3 x, and then plus 1 over 3. Okay, this is going to be quite an important line to use. And apparently this line, the unknown line is perpendicular to this line here, and the unknown line passes through this point here. Now, what we need to do for the unknown line is we need to find two things. We need to find the m value, and we need to find c. So to find the m value, if you have a perpendicular line, you take the gradient of the perpendicular line and you take the gradient of the actual line, and when you multiply them by one another, your answer will always be -1. So the perpendicular gradient is 2 on 3. So that's 2 on 3 there. I go times by m, and it's equal to -1. So m, the gradient of your unknown line, is going to be -3 on 2. That's just from transposing. Okay, so far what we can see is if we fill in information about our unknown line, we know that y is equal to -3 over 2 x plus c. And then we use this point here. So using -2 and -1 to find your c value. So you just have to substitute in y as -1, and for your x value, substitute in -2 plus c. And then just by rearranging these, so -1 equals to, that and that cancel, that's going to be 1. -1 times -3 is just 3. And c is equal to -4. So therefore, our equation of our unknown line is now all known. The m value is -3 on 2, x minus c. So that's our equation for y. We have now found the equation of the line, which was the purpose of the question. Okay, so question 7 is kind of a very similar concept where a line, we don't know the line equation, but we do know now it's parallel to this equation and passes through this point here. We have to find the equation of that unknown line. So once again, we're going to deal with this equation here. We're going to need to extract the gradient from it. So we need to move both this term here and that term there over to the other side of the equal sign. When we do that, it becomes negative 3x minus 7, and then we divide everything by negative 4. So 3x over 4 plus 7 over 4. So that's our line. Now we know that our line is parallel. So parallel lines have the same gradient. As opposed to what we just did before, where perpendicular lines, the two gradients become, when you take the product, they become -1. Parallel lines have the same gradient. So we can now find the gradient of that known line. So m is equal to 3 on 4. And we know that our unknown line, this one here that we're trying to find, has exactly the same gradient. So we can go, okay, well, y is equal to 3 on 4, x plus c, which we do not know. But now, using the point -3 and 0, we know what point the line goes through, so we know that y is 0, and 3 on 4 times by -3 plus c, c becomes equal to 9 on 4. And so therefore, our equation, y equals to 3 on 4 x plus c. So that becomes our line. Okay, so our final question of this series is sketch the graph of here, this. Okay, so what we need to do, it's already nicely factorized for us, so we need to make y equal to 0, and then we've got negative x cubed, x minus 2, x plus 3 squared is equal to 0. And when we find the solutions, I'm going to say that x cubed, just using null factor, negative x cubed is equal to 0, which is the same as just saying x is equal to 0. The negative is going to cancel out with the 0, and when you cube root x and cube root 0, you're going to get an answer of 0. So then x minus 2 is equal to 0, so that means that x is equal to 2. I'll write next to that, because that cubed does have an effect on the graph, it's just going to be a point of inflection at that location at x equals to 0, whereas this is going to be a linear factor when we sketch it. And then finally, our last solution, x plus 3 squared is equal to 0, gives you an x value of -3. And that's actually a turning point form, because you have the squared, so it's a quadratic. So these are our solutions. Now, I'm going to draw in a different color. So we have a solution at x equals to 0, we have the solution at x equals to 2, and we have another one at x equals to -3. Okay, and I want to know, it's not worth finding our y-intercept here because we already know what it is. It goes through 0. It might be worth finding another coordinate though. Find another coordinate. And the reason for that is because we want to know what direction, coordination. Okay, that's... we want to know what direction this graph is going in. So it might be worth finding, okay, x equals to -1, putting it into our equation, p of -1 equals to minus, I'm just putting in -1 cubed. Probably you haven't chosen the best of values, but -1 minus 2 -1 plus 3 squared. Okay, so -1 cubed is -1. We have two negatives there, so that's just going to be +1. They will cancel. This part here will become -3, and this part here will become 2 squared, which is 4. So the whole thing is going to be -12. So we know that when we're at x equals to -1, the value is going to be -12. So if I make these 1, 2, 3, 4, I'll just put it here. I'll put a point -1 and -12. It's not very visible, but it's there. Okay, so now we can just connect all of these points. We know that at we look back at our solutions, we know that at x equals to -3, we have a turning point. So -3 and 0 here is 0, 0. And this point here is 2 and 0. So that's a linear. We have to go through this point here. So actually our graph won't be turning around here, because then it would have to go back up and it will never reach that point. So our graph is starting off like this. It's hitting that x equals to -3 solution, turning around. We can say it's going back through there. There's a point of inflection at this spot, and then it cuts through, right through. That is probably the worst graph that I've ever drawn. But what's important is that you have a point of inflection right here. You need to show that that's a point of inflection, which my graph clearly does not show. But yeah, so hopefully your graph is much better than that. And then you have a linear section here, which you can see that goes straight through the axes, straight through the x-axis, and this is p of x. Okay, so hopefully that gives you an idea of how to sketch polynomials, higher order polynomials.